What's up, students? Hope you're having the best day of your life today. Today we're going to talk about one of the two types of waves that we're going to see in physics, and that's going to be the transverse wave. I'll make another video about longitudinal waves, but the transverse waves are definitely going to be the most common types of waves that we're going to see. This is going to be part of an entire waves playlist, so some things are going to overlap. Some things will be a little bit more detailed than others, but by the end of this video, you'll have a pretty good idea of what transverse waves are, the difference between a pulse and a periodic wave, how pulses reflect off barriers, and then the characteristics of periodic transverse waves. So those are going to be frequency, period, amplitude, wavelength, phase, and speed. This video is going to be great for anybody that's taking like the SAT physics exam, AP Physics 1 even. It's a great intro there. The Regents level here in my home state of New York, or any basic physics class that you're taking for the high school or early college level. So the first thing I'm going to do is I'm going to draw a transverse wave, and I put the graph paper up here so I can kind of graph it and have it be pretty to scale. So let me just draw this real quick and then I'll come right back. All right, so this is the best sine curve I can draw. And a transverse wave, guys, it looks like a sine curve or a cosine curve depending on where you start your axis. And one thing I want to define, I'm going to define the direction of motion. So the dom of this wave is going to be in this direction here. Now, the thing that makes it a transverse wave is that the particles in this wave, so we have, this is the equilibrium line right here, equilibrium. So that was if there is no vibratory disturbance, right? We know that a wave is a vibratory disturbance that only transfers energy and not mass. So if this was the equilibrium before the particles are being vibrated, now we have this maybe a rope or string or air or something that these particles are being vibrated as the wave moves this way. So no particles are moving this way, just energy. So essentially we can draw all the different particles of this rope or string or whatever it is that's moving, okay? And the reason I want to show you this is because what these particles are going to do in relation to the direction of motion is what's going to define it as a transverse wave. So in a transverse wave, the particles move perpendicular to the motion. So the vibratory disturbance of these particles is going to be up and down, okay? And we can see that if this is the motion, right, this is perpendicular to that motion of the wave. That's essentially what the definition of a transverse wave is, where the particles, they move perpendicular to the motion of the wave. And a lot of times they're going to ask questions like, let's call this point right here. Let's call this point A. And they'll say that 1 instant later, is this point A going to be higher, lower, or in the same position? Well, if I were to shift this whole wave a little bit to the right, I think of it as this point right here is going to be lower. Soon, this point right here, or this particle energy of the wave, is supposed to be over here. So when you have to define, is this point going to move up or down? Is this point going to move up or down? Look at where you are on the wave. We have to think about what's going to happen to this particle as the wave, this whole thing, starts to move to our right. And we're going to be able to define that once we know a couple other characteristics. Now, what we're seeing here is what we'd call a periodic wave. And this is when there is a constant vibratory disturbance. Okay, so you can picture like a wave generator, and if you're in my class, I'm going to show you exactly what this means. But essentially, I can just have a pulse, which would just be one wave. So like if this was a rope, I could send one vibratory disturbance down this rope, and it would travel this way all by itself. This is a pulse. So a pulse is just one disturbance. But now what happens as this pulse or as this periodic wave travels, if it were to say hit a barrier, so we'll call this some sort of barrier over here, waves are going to reflect in the opposite direction. So the reflection of this pulse going back the other way would look something like this. So the reflected waves are opposite. Now, the size of the wave, that's called the amplitude, which I'm going to talk about in a second, that's going to be the same. So essentially, I'd have a wave that's going to come down, it hits the wall, and then it would travel back on the bottom of this wave. The same thing would be true here. If I had a barrier over here, it would bounce back, and it would be the opposite, and that's going to be called a standing wave, and that will be for a later video. But what you need to know now is that a periodic wave is going to be one hump after another, where a pulse is just going to be one hump and it's going to travel all alone by itself. And in both of these, when they bounce off a wall, they are going to reflect in the opposite direction. Another way we could say that is we could just say that the wave is inverted. Now we can look at some more characteristics. So if we look at the characteristics of this wave, the first thing that I want to talk about is the frequency. Frequency, guys, is given as a lowercase f and as a unit of hertz. Ouch, that hurts. Jokes. And essentially what the frequency is how often or how many waves go by a given point in a certain amount of time. And that makes sense, right? Like we know frequency, the frequency at which something happens. How many or how often does a wave go by in a certain amount of time? So if I were to look at this point right here and I were to start my stopwatch, ready, go, and I counted that there was 3 waves that went by, I would be able to find the frequency of that wave. So a hertz sometimes is also written as a 1/seconds. So we can say this is the amount of waves in 1 second. So I click my stopwatch, 3, 2, 1, go. I count 5 waves in 1 second. The frequency is going to be 5 hertz. And the frequency gives a transverse wave some of its properties. Now, the most common transverse wave that we're going to talk about is light and the rest of the electromagnetic spectrum. But frequency is going to give light its color, where when we talk later about sound, it gives sound its pitch. So frequency definitely adds to the characteristic of a wave. Now, one that ties right into this is period. And period is given as a capital T and it has a unit of seconds. And this is how long. We know like a period in school. How long for one wave cycle. And one wave cycle, guys, is 360 degrees or one full sine curve or one full cosine curve. So if I time how long it takes for one complete cycle to go by a given spot, so I start here, I wait for 360 degrees of a wave to go by, that's going to be the period of the wave. And these two are going to be related in a formula that's given on the Regents reference table and as well as the AP reference table, and that's period equals 1/frequency. The next characteristic of this wave is going to be something called the amplitude. And we measure the amplitude from the equilibrium position to something that we call up here as the crest. And down here we call this the trough. So amplitude can be measured from the equilibrium line to a crest or the equilibrium line to a trough. And guys, this is something that gets confused with students all the time. From crest to trough is not A. So students will confuse this. We have to make sure that we go from the equilibrium line to a crest or some equilibrium line to a trough. That is the amplitude of the wave. And the amplitude, it does not affect speed, it does not affect frequency, it does not affect wavelength and all the other things we're going to talk about. This really, it just carries the energy. So amplitude carries energy. An example of this in light, like we said, frequency in light was the color. Amplitude makes light brighter. A brighter flashlight just has a higher amplitude than another flashlight. In sound, frequency is going to be the pitch, but in sound, amplitude is the volume. So essentially when you turn up the volume, you're really just raising the amplitude of that sound wave. And even though I'll probably say this in other videos, maybe I'll just put this in case you're seeing it. So frequency for light, it's going to be color. And for sound, it's going to be pitch. And up here, when we get to amplitude, for light, it's going to be brightness. And for sound, it's going to be loudness. Now, guys, obviously there's other types of waves besides light and sound, but on a basic physics level, these are going to be the ones that we're going to talk about more. Like, for example, if we talk about an earthquake wave, which is a wave, we're not going to be talking about amplitude in terms of brightness and loudness, right? These are just the ones that we're commonly going to see, and I will talk more about amplitude in other future videos when we're not talking about light or sound. I'm trying to use all different colors here so we can see and I can use the same picture, but the next one is going to be wavelength. Now, wavelength is given by the Greek symbol lambda, which is really looks like an upside down Y. You can draw it very simply just by doing an upside down Y. That's perfect. Everyone has their own little flair. And it has a unit of meters, guys. It is a length, and it is defined as 360 degrees apart. So 2 points that are 360 degrees apart, that is going to be one wavelength. So depending on where we start on this wave, and I'm going to use brown because I know it's getting a little sloppy, if I were to count out degrees of this wave, and you learned about this in math, right? This is going to be 90 degrees. This is going to be 180 degrees. This is going to be 270 degrees. and this is going to be 360 degrees. So from here all the way to here, that is going to be one wavelength. Now, this gets a little bit confusing because if I have a periodic wave, right, there may be a bunch of different waves in a row, but we still have to be able to measure the wavelength. So for example, if I started here, this would be 90, 180, 270, 360 would be up here. So I can go from crest to crest. That's one easy way to do it. Go from crest to crest or go trough to trough. So those are common. And then also one sine curve or one cosine curve. Those are all different ways that we can measure a wavelength. Now, let me go to a different page. I'll sketch one real quick to show you what I mean when there's multiple waves. So real quick, this is the amplitude of the wave, right? This is also the amplitude, and we'll say these are equal, drawn scale. Like I said, I just sketched it really, really quick. But let's say, for example, I have from here to here, I say this is 6 meters. And I want to know what is the wavelength, okay? Now, to do this, most kids intuitively just want to shoot to 6. What we need to know is we need to know the number of cycles. So I'm going to see how many 360 degrees I have. If I start here, this is 1 cycle, this is 2 cycles, and then to here is just 1/2 a wavelength. So in this 6 meter area, I really have 2.5 lambdas. So 2.5 lambdas equals 6 meters, right? So how many are going to be just 1 lambda? Well, that would mean I'd have to divide each side by 2.5. And I would get lambda equals 6 divided by 2.5 meters. And you guys would have a calculator and you could do that a lot quicker. I'd make a fool of myself if I tried to do that math quickly. But just remember, in a periodic wave where there's multiple wavelengths, if they give you that whole length, lambda is just one 360 degree cycle, and that's it. So let's just use these degrees one more time. 90, 180, 270, 360. The last thing I want to talk about is phase. And phase we're going to talk about more when we get to interference of waves, meaning when two waves are taking up the same spot. But essentially, I can shift this whole wave, and we'd say I'm going to shift it by a phase of a degree. So waves are in phase if they start and stop at the exact same spot. But I can also shift this way. So for example, if I want another wave to be 90 degrees out of phase with this, I would come 90 degrees and then I would start my wave, which is pretty hard to do. Actually, I'm getting pretty good at it. So essentially, this is what this wave is going to look like. Now, these two waves would be out of phase because they do not start and stop at the exact same spot. So whenever we see phase, we're going to be talking about 90 degrees, 180 degrees, some sort of degrees that the start and stop of two waves are going to be happening. Now, like I said, that's going to happen more in interference, so don't get too stressed out about phase just yet. But that's what we're going to be looking at, the degrees of two different waves. We can also look at two different points and see if those 2 points are in phase with one another. So if I have this point, this point, this point, we'll call these A, B, C, D. Now, if waves are in phase, they start and they're doing the exact same thing at the exact same time. So at point A, I have the wave that's about to start going upwards. At B, I have a wave that's about to start going downwards, about to start going upwards, about to start going downwards. So the points that are in phase are A and C and B and D because they are both in the same position on their waves. This is midway through a wave at 180 degrees. This is midway through a wave at 180 degrees. Now let's take a look at an example and see how I can show you one picture and we can answer everything that we need to know about transverse waves. Okay, now let's just pretend that I am the best sine curve drawer ever. It's easier when you do it quick, whatever. So given has a frequency of 2 hertz. This whole entire periodic wave has a length of 6 meters. And this is given as 2.4 meters. And then here are the questions that I'm going to ask. And pretty much you can pause this video and go through and see. But if you can answer these questions, you are very, very good to go. What is the amplitude of this wave, guys? Remember, amplitude is from equilibrium. They want you to put 2.4, but it is really 1.2 meters. Wavelength, we have to see how many waves. So we have to go 360. Here's 1, here's 2, and here's 3. There's 3 waves over 6 meters. That means each wave is going to be 2 meters long. That is going to be the wavelength. Period, as I told you before, is given as 1 over f, which is just going to be 1 over 2 hertz. And 1 over 2 hertz is going to be 0.5 seconds. For the speed of the wave, we are going to need a formula I have not given to you yet. I figured I could just show it to you right here because it's nothing crazy. The speed of a wave is given by the frequency of a wave times wavelength. Now, some speeds of waves are constant. The speed of sound is constant, and also the speed of light. But in general, when I want to find a wave speed that is not the speed of sound or the speed of light, I would do just frequency times wavelength, and I've just figured that information out. So the frequency of this wave is 2 hertz. The wavelength of this wave is 2 meters. That means that this wave is traveling at 4 meters per second. And for my students here in New York, this formula is given on your reference table. Give 2 points that are in phase. I can look at any 2 points that are 360 degrees apart, and I should be pretty good. Like I said, generally what I'm going to do is I'm going to label them. These are about to go down. This is about to go down. This is going this way. This is going this way. This is going a little bit up. This is going a little bit up. This is going a little bit down. And this is going a little bit down. And this is going a little bit up. Now, sometimes a little bit up and a little bit down doesn't really help that much, but it might if we can see. There's nothing that's really 306 degrees apart from A. So nothing's going to be good with A. B is on the way down a little more, a little bit before halfway, right? This is halfway of this wave. So is this. So B and G, they're in phase. Now let me just see if there's anything else. C, that would be something over here or something over here. Nothing there. These two, so B and G in this case are the only ones that are in phase. Now last is what I was talking about earlier in the video about which direction is each going to move. Like this is a snapshot of a wave that's in motion. The direction of the motion is going to be this way. And I'm going to give you a little bit of a trick on how to do this, guys. What I do when I need to know if this H is going to travel upwards or downwards, what I do is I go to the nearest trough and I draw like almost like a little bit of a wall. And you could do this imaginarily in your head, or you can actually draw it on a diagram. That's not that big. I go to a trough and I draw a wall. And I pretty much say, okay, what is the next thing that's going to hit me? Is it going to be a crest wall or is it going to be a trough wall? And the next wall to hit point H is a crest wall. And a crest is upward. So H is going to go up. And what I mean by like what's the next wall that's going to hit me? For point F, the next wall, if the direction of motion is this way of the wave, the next wall is going to be a trough wall. So F and E, in the instant after this, they're going to travel downwards. H and G are going to travel upwards. If I continued on and I drew another crest wall, all of these points here are going to hit the crest wall, so they're going to go up. So they're definitely going to ask questions like this, guys. I hope that gave a pretty good understanding. If there's anything I left out, please leave it in the comments down below if you need to fact check me or whatever. Sometimes I do make mistakes, especially in a long video like this. Until I catch you on the next one, guys. Enjoy your physics journey, and I'll catch you on the next one.